idea, this definite integral. And definite integral, all it means is it has what we call bounds, a and b. So it has a beginning and an ending point. Remember, when we think about this integral from a to b of some function f, we're talking about a starting value, an ending value, and we're talking about adding up the space underneath. So this adds the space between f of x and the x-axis from x equals a to x equals b. That's what it does. Now, so we got to kind of think about what that does. This is what's called an accumulator. Now, I'm gonna do a couple of examples with this, but I want to kind of unpack this idea of the chart, because when we think about the chart, we think about integration and differentiation, and we think about the chart, and I know I've always labeled it f, f prime, f double prime. But what if I don't label it f, f prime, f double prime? What if I just leave it blank and I talk about in general what's happening? Meaning if this is positive or this is negative, this column would be increasing, this column would be decreasing. And same thing goes down here. You know, if this column is positive or this column is negative, then this column is increasing or decreasing. Now, I know generically we've labeled it f, f prime, f double prime. But in general, what we think about doing is going, I'll draw it in a different color. When we think about going this way through, it's differentiation. Okay? If we go the other way, that would be integration. So when we're talking about, you know, what does this kind of look like, is what if I labeled this right here F. Let me just pick a different color. What if I labeled this column F? Then it should make sense that this column would be the integral of f. If I labeled this one f of x, this one would be the integral of f of x dx, because if we integrate, we're going back with the red, but if we differentiate, we're going forward, and the integrals and derivatives undo each other. Well, that would make this one f prime, right? Or another thing you could think about is this one would be the integral of f prime, because again, we would integrate. So if this is f prime of x dx, then the middle column is the integral of f prime. So we can kind of move through these in general. So we can relabel these anything we want. What that kind of brings us to is it brings us to a thing that's called the second fundamental theorem. And we will get to the first fundamental theorem, but I think it's easier to unpack this second fundamental theorem. And the second fundamental theorem basically says that if we integrate from a to some value x of a function f of t dt, if we then differentiate it, those two things should undo each other. The derivative, remember this is the derivative, this is the integral, So if they are truly opposites, they should undo each other. You should just get f of x. Similarly, if you integrate f prime of x dx, you should just get f of x. That's kind of what we're talking about up there in that chart. So we got to think about how that works when we're doing some of these problems. For example, let's take a look at this one. So when we're asked to do this, it's given this function below, and it says, find the value of g in simplest form. And g is defined to be this integral. We're supposed to find the value of g of 5. Well, g of 5 would be the integral from -5 to 5 of f of t dt. Notice that I'm giving you the graph of f. And if we think about what this means, this means that we're talking about integrating from -5 all the way up to 5. Now I'm going to highlight these in colors because I want you to think about what's happening. Notice that this is the graph of f. So when we integrate, since in this part f is negative, and in this part f is positive, when we think back to our chart, that means we need to have our integral needs to decrease, and then our integral needs to increase in value. So that's why that space below the x-axis is really a negative accumulation, and the space above the x-axis is a positive accumulation. Because when you think about back up to the chart, we're given this middle column, and when that middle column is positive, the integral would be increasing. If that middle column is negative, the integral would be decreasing. So we take something like this, and we're just calculating these areas. If you think about like the area of this, it's a triangle. It's 1/2. The base of the triangle is 4. The height of the triangle is 4. So together, this has an area of 8. But because it's below the x-axis, it's got to be negative. And we're going from, notice the direction that we're going, because that matters. We're going from -5 to 5. So we're going in this direction when we're accumulating this one. Now, similarly, if you take this one right here and we think about what that is, notice that that's a triangle as well. It's a triangle that's 1/2. The base of that triangle is 5. The height of that triangle is 2. So together, the area of that triangle is just 5. That means if we were going to calculate this value g of 5, we would have the negative space from the first triangle plus the positive space. Together, that's -3. So that's how you might calculate that integral. Hopefully that makes sense. Now, it matters which direction you're going. I drew this arrow down here because that really does play a part. Because when we think about something like this one, well, this problem is saying find f of -6. That would be the integral from -1 to -6 of g of t dt. Notice we're given the graph of g of t. Well, now when we think about what's happening is we're starting here, and we're going back this way, all the way to -6. But when you think about like doing this amount here, this value is negative. But because we're going in that opposite direction, think about what would happen. Think about from -6 to 1, what the graph should be doing is it should be going down. So when we add up this space from -1 to -6, we should actually get a positive quantity. And let me show you what I mean by that. If you think about, so if you think about this area, so this area, if we calculated that area, one way we could do it is we could calculate it by counting boxes. 1, 2, 3, 4, 5, 6, 7, 8. Together, this is 9. So the area on that is 9. Now, we need to think about f of -6 in this problem is actually positive 9. It's actually positive 9 because when you think about like what would happen is even though that's negative, because we're going in this direction, we need to kind of think about what that does to that area. It's negative, but because we're going in a negative direction, this is a negative direction, that then the area becomes positive. That space becomes positive because we're starting at -1 and we're going to -6. And so that's that kind of double negative. So that means that f of -6 is actually 9. Hopefully that makes sense. If it doesn't, I'll try to explain it a different way if you come to office hours or ask me questions. I want to jump to the last example because I think it's the easiest one to kind of go through, and then we'll go back to those other examples. But and I'll put these notes up on Schoology if you want to print them out rather than copying them down. I maybe should have said that at the beginning, but anyway, if you think about this last one, G. So let me do this in black so you're not confused about my color coding. G of -7. G of -7 is the integral from -7 to -7 f of t dt. Notice if we start here and we end here, we have gone nowhere. So if we start there and end there, the answer to this has got to be 0 because we've really done nothing. We haven't gone anywhere. We haven't accumulated any area. We just stayed at the same place. So the value of that is just 0. Now let me go back up here. Let's look at this one. Actually, let's look at this one right here. Notice we want to find f prime of -1. So if this is f of x, then it should make sense that f prime of x would be the derivative of this. Now, if you think about what derivatives and integrals undo each other, then f prime of x must just be g of x. So f prime of -1 is just simply g of -1, and g of -1 in this case is, since this is the graph of g of -1 is just equal to 0. So in this case, it's just equal to 0. Final example I want to do is this one. Now we're asked on this one what g double prime of -1 is. Well, g prime of x, again, would be that derivative of that integral. Well, if you differentiate an integral, you should get just the normal function. So then, if you take the second derivative, if you differentiate it again, then you should get just f prime. Remembering, that's just the slope of the graph of f. So when we're asked to find g double prime of 1, that's f prime of 1, and f prime of 1 is right there, and that f prime of 1 is undefined because it's a sharp change, or we could just say does not exist, because that's a sharp change in the graph. But this idea of where do these things line up is a really important thing. I'll do some more examples from the assignment, but this should get you kind of started on that first section of the assignment.